Strings are bad, okay? Well, more specifically, the perils of dynamically allocated memory in constrained memory environments such as the Arduino. Today, in Mikey's lab. Whenever anyone starts using an Arduino or any of the other maker microcontrollers, invariably they find themselves using a string library. And while on the surface this may seem good because it does make dealing with strings a crap ton easier, there's a lot going on in the background that you don't know. And most of the time when you think you should be using a string library, you shouldn't. We're going to talk about this today. We're going to talk about dynamic memory allocation, how the memory is structured inside of an Arduino and your full PC technically too. We're going to talk about where variables go. We're going to talk about how they are allocated and what the best way to manage the memory for your projects are, and some of the consequences of doing it wrong. So lab code up. We're going to learn something today. I've recently had an experience working on an Arduino project that ran very close to the 2K maximum amount of memory that is on the Arduino. I'd originally used strings in this particular project because I was lazy and it was easy. As I found out, I probably shouldn't have done that. It did produce some radically unstable code and caused the Arduinos to actually crash, which should result in a reboot, but because of the way that this happened and because of the memory corruption, they just froze. I don't need to explain why this is bad, but it's bad. Alright, so let's talk about the data structures that are inside of an Arduino or any other microcontroller, and even your full PC. Okay, the first thing we have is the data structure. The data structure is a fixed size. It starts at the bottom of the memory address structure, and everything, all the globals, all the includes, wind up in that area. It doesn't grow, it doesn't shrink, and everything that's within that memory has a global state to it, so it never goes out of scope while you're programming. The next one we're going to talk about is known as the heap. The heap is a dynamic area of memory that can grow and shrink. It is located directly on top of the data and grows upwards as you add to it. The heap is an interesting thing. We'll dive a little closer into the heap and the stack in a moment, but let's talk about the stack for a second. The stack is an orderly piece of memory that starts from the top of the addressable memory and grows downward. The stack is always very deterministic as to what is in there, and the order in which things are allowed to go in and out of the stack is very precise. Anything that is declared inside of a function, so just one step below the global scope, winds up on the stack. Okay, so let's talk about those two sections, the stack and the heap. Obviously, data, which as I've mentioned before, is where you want as much of your information and as much of your variables to go because it stops the chance for memory leaks. It makes your memory usage very stable and very predictable, which in a low memory environment is, well, perfect. So, if we're going to talk about the stack and the heap and the differences between them, I'm going to need a prop. It's time for some crackers. Just bear with me. So we're going to start with the stack, talking about the stack. And just like you might assume, the stack is like an ordinary, orderly stack of crackers. I can take another variable, I can stick it on the top. I can take a variable off the top and remove it from the stack. I can't pull one out of the middle because it will cause the stack to collapse. This is very much like the stack memory that is in your system that you're building. So if we have, let's say, a 2-item stack and we call into a function which declares 2 variables in it. So we put 2 more crackers on the stack. Right, those are the 2 new variables. Then inside of that function, before this function goes out of scope, we call into another function which adds another 2 variables. So now we've got 6 crackers here. Okay? the function that we called into last exits, which means everything that was inside that function goes out of scope, and we pull 2 crackers off. We're back down to 4. The initial function that we dove into, right, exits. Pull 2 crackers off, because those variables went out of scope, and we're back to the base amount. This is essentially how the stack works. For the heap, I'm going to need to switch cameras a little bit here. So, now we're talking about the heap. The heap is more like a line of crackers on the workbench. Okay, so we have 6 crackers here. And right now, it's nice and orderly. Okay? I can pull a variable out in the middle and take it off and deallocate that space, and then this memory becomes free. I can throw another variable into that space. So basically, if I have a 6-item array like this, and then I pop 1 out, let's say. So I deallocate this variable. The next time I go to allocate a variable, it's going to look for a memory size where this variable will fit. So it starts over here and starts going all the way through. When it finds one that it will fit, it will drop it in place, and once again we have a nice orderly line. But what happens if the variable is a different size? So for example, we'll pop this variable out, and we'll take some memory away from it. Delicious memory. So now, the memory allocation system takes this, and starts scanning, looking for a place that it will fit. And it goes, oh look, it'll fit here. Okay. So now we have our 6 elements again. They're on the heap. Right, we do have a gap here. But the next thing that comes along, let's say, is a full variable. Right? So now it comes here and it tries to find a place it will fit. It won't fit in that little bit of memory, so it allocates over here. So now we've essentially made this memory useless until something that's small enough to fit in there will get there. So now let's do that a couple more times. So we pop a variable here, right? We add a smaller variable back in. Pop a variable here. Add a smaller variable back in. Let's try to add another full string. And if we go through, well, now there's nowhere to add the string. So what happens is these little pieces of memory wind up with something that I call heap creep, where the end of the heap starts to creep towards the end of the stack. When these two meet, bad things happen. Like cross the streams bad in the world of your microcontroller. How it's going to react is anyone's guess. You could wind up back into, let's say, a call into a function where you're in a for loop, where I, or whatever variable you've chosen, isn't initialized. So you could wind up running an instruction that was supposed to run 5 times, I don't know, 32,000 times. If your counter's a 16-bit integer, which it probably is. So with the string library that I refer to, I'm going to bring this back. Inside the string library uses malloc and free a lot, which is dynamic memory. So this structure starts to happen the more you use the string objects. So I know what you're saying. If I'm not supposed to use strings, how am I supposed to do this? Well, the short answer is car arrays. The long answer is a little more complicated. So let's start looking at some code. I'll show you what I originally wrote, and I'll show you the better version, and we'll talk about why. Right now I gotta get rid of this tasty evidence. Oh, fine. So the first one that we have is a function called parse return code. And the parse return code takes a string parameter, which is bad for 2 reasons. I'll talk about that in a second. And what we're doing, if you read the code, we're looking for a line inside of the response that is +SBDIX : space. This is very specific to the project that I was working on, so don't worry about it. We're looking for a substring. We're trying to extract one value from the middle of a string. This is a fairly common thing that's done with the string library, and this is how you would normally do it. And that's to pull out a substring based off of the index of things inside of the string. The problem is this is going to create a lot of duplicates of a string. And then what we do is we return the response using a toInt function. Again, an uncommon use of the string library. But let's take a look at how simple this is using car arrays. And we'll also talk about why passing the string response was the wrong answer. The good version, as you can see here, has an int function, parse return code, that takes a character pointer to the response string. First off, let's talk about the pointer. The first version passed the value by copying it in memory. So it created a second copy of something we already have in memory, which is pretty inefficient to begin with. Now, as I said, I'm being harsh to this code, but I wrote this code. This was my code, right? I was being lazy. I was trying to do this as quickly as possible, and it bit me. And I want you to avoid what bit me. So by passing a pointer, what we're actually passing is an address in memory where the value is. So we're not copying memory, we're not storing the same thing twice. We're saying, hey, look over here to find out what I want you to work on. From there, we use a standard built-in function, stir, right, to find that substring that we were looking for before. This will do all of the stuff that the index of did without using dynamic memory. This is a very deterministic type of memory. We know exactly where this string, this character array is. We know exactly how big this character array is. We're not duplicating it. We're just working with it. Okay? So we found the start of this, and then we tell the pointer start to move 8 memory locations forward. Now the pointer knows that it's pointing at a car variable, which is 8 bits. So what it's going to do is it's going to go, I'm supposed to move 8 units forward. So 8 times 8, I'm supposed to move 64 bits forward in memory and start from there. Then we use a function called a2i, which is text to integer. One of the things I recently learned about this, when I rewrote this, is a2i will automatically stop at the first non-numeric character. Really handy. Really handy. So we use a2i to convert it to an integer, that little substring, based off of where we found the start plus 8 of here. So we've taken this hard to read piece of code and we've created a 3-line function that does what it did before without using dynamic memory in a very deterministic way and created something that's a lot more efficient. The second example I have is an exchange between the module and my program for starting the communication of the satellite. The function is called startSatCom, ironically. Well, not ironically. You should name your functions things that make sense. Okay, so the first thing that we do is we send a command to the module. Right, and this command takes a long time. The longest I saw it take was 30 seconds. Average I saw it take was 20 seconds. So the example that I saw said that I should wait the 30 seconds. Alright, so we wait 30 seconds, printing a period every second so that I know that the program is still running. And then if there is satellite data available, we read the string in. Okay, so read string returns a string. So this resp is a dynamically allocated variable that is in the heap. I don't know where in the heap, I just know it's in the heap. And then we use our parse return code function that we talked about before to return the number from it. So again, this was passing with direct copy. This was just taking massive amounts of data that I don't know what it's doing and throwing it around. Okay? Once we get the response back, we obviously do the return code and look through. So let's take a look at what this function looks like when we're using memory in a better way. So once again, we do the standard send the message to the satellite receiver to start the exchange. Right? We wait at this point I have a 45-second timeout there. I don't know why I elongated that, but probably through troubleshooting. Right? And now we say that while sat is available, right? And we have less than 200 characters. The response to this command should always be less than 200 characters. So one of the things I missed, if we go back up to the top here, you see I declared a static buffer. If we go back up to the top here, you see I declared a static buffer of 200 characters. right? So we're being very deterministic in how much memory we want to use. Yes, that's big, but remember, this is on the stack because it's a variable in the function. It's not in the heap, right? So we go through the satellite's response reading 1 byte at a time, using sat read as opposed to sat read string, and we make sure that we only accept less than 200. Okay, then we send it to that parse return code function that we saw with the 3-line optimization. We get the integer back, and the rest is the same. The beautiful part is we know that as soon as this goes out of scope, that 200 character buffer is pulled from the stack. Now, this example I wanted to show you because when you're dealing with car arrays and strings and you're trying to mix them, sometimes copying information back to each other required some finesse. So when you try to add data into a car array, sometimes it can be a little harder than you think it should. So for example, in our bad example here, in ISR test, we have a string message text, which has the text that we want to send to the satellite module to be bounced off of the Iridium satellite network and back into an email to come to us. We have a bunch of other variables that are part of a message structure. And then when we want to copy the data in, we're doing a message to car array call, right? Which is, again, a string function that converts the string into an array of characters. Again, we don't know what the memory allocation in the background is, whether it's copying memory again and referencing and passing pointers. We don't know. I assume that the standard C string library is well enough written to not have any leaks in it. But again, you're risking the heap creep. Right, and then we add the message to the queue and we send it. So what does this look like in the good version? Well, in the good version, right, we use a command called sprintf. Sprintf will allow us to take what appears to be a string when we're programming and have it spit out as a character array. Right? So sprintf takes the first parameter is the character array buffer that we're going to put the string into, and then the string that's going into it. So this is going to create an array. This is going to put this string into this array. And that very important. Sprintf, scanf are very useful functions with this. There's many more functions that are out there. If you want me to go into detail as to any of the specific functions and how to accomplish anything that I've talked about here, just ask. I'll be more than happy to. So yeah, this is the primary reason why dynamic memory allocation in a constrained memory environment is bad. And it comes down to not really knowing what's going on in the background. The heap creep example that I showed you with the crackers of data just moving and getting bigger and bigger and bigger without actually allocating any more data. With dynamic memory allocation, you can theoretically do everything right and still lose. So if you're just starting out with Arduino, if you have light examples or light experience with Arduino, you really should start to move yourself more towards a car array and a more deterministic method of dealing with strings. The string library is tempting. I've fallen for it myself. It's just so easy to declare a string and use one of the built-in functions, and away we go. And I'll be honest, in a lot of applications for the Arduino, this would probably be fine, given how little of a runtime the project has to have, and given how many projects actually get near the 2K limit. This particular project that I'm working on needs to have a 4-month runtime, and it currently is using 71% of the 2K that is available at boot. So that's a lot of memory. So I can't afford even the smallest leak given that amount of time. I can't afford for this to freeze. It has to run, and it has to run flawlessly for months. And if you want to write that level of code, you need to do it this way. One of NASA's programming standards says that dynamic memory allocation cannot be done. It's one of the things that they do to ensure that everything that is going on inside of a spacecraft is deterministic. Why is that important? because lives are on the line. So listen, I hope you learned something today. If you have any questions, go ahead and put it in the comments down below. If you haven't already, click that subscribe button. If you liked the video, smash the like button if that's what you're into. Right. Thank you for joining me in the lab, and I will see you next time.